As per the lecture plan that I have here, it is the lecture number 11, and but this lecture I have it available for you in the recorded form. In this lecture, I will discuss on the topic active power frequency control, which will be part 1, and here in the part 1 discussion will be on how to model the system for frequency control application, and we will also discuss about the frequency dynamics here. So this is the part of the lecture which I have it here for you, and so we'll start with the lecture, and I hope you can see my screen. So this is on the topic active power and frequency. Mainly we say sometimes as speed control. So, and here in the part 1 discussion will be mainly referred to the primary control. So in respect to the components which we have in the power system, and then more specifically when we say about the generator, and so here you see is the generator part, the machine. This generator is connected through a network, a line it could be, and then the network also has a load connection at the other end. Then the generator is coupled to the turbine, which will be a mechanical turbine. Thus, this side of the components, which you have it here as a mechanical system. So this is the turbine, and then depending upon the type of the turbine, you may have a steam turbine. So in that case, you have the steam inlet to the turbine, or if it is a hydro turbine, then it will be a water inlet to the turbine. So for the case shown here, you have the furnace and the boiler, where you have the conversion of water into steam, and thus the combustion process takes place, and then you get a steam at a much higher temperature and pressure from the boiler, and which is injected on the blades of the turbine to have its mechanical work done. Then to input to the furnace, you have it could be the coal or maybe the oil as well. So this is the supply side, the fuel source. Now, these are the components which you refer them as a mechanical system, and then on this side you have electrical system. Now, in respect to the generator, when you look at, we have voltage control, and for that, in fact, for the generator, you have an exciter and as well as the stabilizer as well. So to damp out the low frequency power oscillations, so you have the controller, exciter systems, and then the voltage regulator basically, and then the stabilizer. Then for the network line trip, all that part or the network control, you have the relays in operation. And then again, if you want to have the load setting, you can have the load relay, which will have the load setting applied. So you have several quantities, variables. Let's say it could be P. You want to control active power, you want to control reactive power. At this end, you want to control the voltage, and thus the amount of the power flow to the line, to the generator. Then on the turbine side here, you want to control the output torque from the turbine, and as well to control the output torque from the turbine, we have the governor. So this governor will regulate the amount of steam inlet to the turbine here. So we have several stages of control actions in the system. You have speed control, you have the pressure control. Yeah. So this is the overview of these some basic components that we apply in the power system. Here, if you much more in detail, it is shown in this figure. What you have it, for example, this is the control structure that we apply it on one generator set. So controlling for one generator set here. So generator, you have excitation system and control. Then the excitation system will control the field circuit or the field current of the generator. And you can see there is a feedback through from the generator terminal. It is a feedback of voltage signal here. Then for the, as we have discussed earlier, for the low frequency power oscillations, damping of low frequency power oscillations, we have the feedback of a speed signal here. Again, it will be fed to the AVR of the excitation system. Then this generator is being coupled to the prime mover, and then again you have the governor. So here you can see there is a feedback of a speed signal here. It will be to the governor and then to the turbine here. So this is what we have, the control structure applied for one generating unit. And then the generator is connected to your network. So again, you have several forms of control applied on the transmission network as well. So you can see here that we have the reactive power control or the voltage control on every buses in the network. Then as well as we may have HVDC power control, and then again associated control in the circuit or the subsystems for the HVDC network. Now from this at the transmission network, this transmission network could be connected to several other power plants here in the system. So thus you may have the measurement of frequency, then the line that connects to another power plants, and then you have the amount of the power flow to the line, and then what is the amount of power generation. So thus you have the feedback of these signals. And in fact, at another hierarchy level for the control structure, we have a system operator. So where you have the complete information about the generation control to be applied for all the power plants in your network. So here, this at the system operator level, you have all the information about the frequency, power flow in each of the line, and then what is the power generated in each of the power plants. So they get all this information, and then they decide. So here there is a decision making policy, you can say, which is given as an input. So as to apply the frequency, load frequency control, and then again it will be based on economic allocation of the generation on the power plant. This economic allocation is more important for steam turbine, right? And so as you can see, at each generating unit level, there is a control action through the governor for speed, for frequency, you can say, then the several generators, and then the power plants in our network were being interconnected, because this information is also shared with other generating units. Yeah. So that means you have the power fed to the transmission network from several other power plants in the network. So thus, so when we have interconnected systems, so let's say you have two different areas and then being interconnected through a tie line. So with the frequency information and the tie line power information, we also apply load frequency control. So this is the outer loop, or sometimes we say a secondary loop for frequency control applied in the system. So here, this one refers to the local loop for frequency control. That is basically we say as primary loop. And then if the system is interconnected through your network, then here it comes the load frequency control, and sometimes we also say as refer it as automatic generation control when we apply the economic allocation for the power plants, for referring to the frequency control problem. So this is the complete structure of our power network, and then different levels of control action applied here. Yeah, here it could be a little bit more clear way in the figure as shown. So you can see you have your generator, you have the turbine, and then there will be an actuator which will regulate the amount of steam inlet or water inlet to the turbine. And then you can see there is a feedback of a speed signal here to the governor. So here you have the reference speed. And then, so you can see that there is a local loop here. So that is referred to the primary control for frequency for each of the generating unit. Then the generator being connected to your network to connect feeding power to the load, and then again several generators in the other power plants. So you have the information this way, and then you get the frequency information, you have the tile and power flow because the generators being interconnected. So, and then this could be this information, frequency and the tile line power, this could be applied for what should be the amount of generation change being applied on the generator, and thus the output power from the turbine. So thus you have an outer loop here, outer loop for frequency control, and with the main purpose of economic allocation of generation, and then that is to say sometimes we say load frequency control. So here again it is the signal is fed to the speed governor. So but here the information it is exchanged to another area, another power plants to which your generator or the power plant is connected, and then this forms this loop forms the secondary loop or the outer loop control for frequency regulation here. This is the slide to show and so what are the typical control actions or the control loop we apply in the generator. So as you can see, you have the generator, you have the field circuit, and for the terminal voltage control from the generator side, you have the excitation control, and you can see there is a measurement of voltage signal, and then you can say the reactive power or the voltage controller, which will regulate the field excitation in the generator. Then from the generator terminal, you also have the measurement of frequency. And then you have, let's say, what should be the set point for the power from the turbine side. So you have this one, and thus you have the active power and frequency controller to regulate the valve and thus the steam inlet to the turbine. So as such, you have two loops. One is this one, and another is this one here. So for each generator, we have the frequency control loop, and that will be either in the primary loop or the secondary loop with the LFC applied, or then another one is for the voltage regulation or voltage control. That will be through the automatic voltage regulator to control the voltage at the generator terminal, and thereby the reactive power output from the generator here. So these are the basic control loops applied on the generator. And here it refers to because your generators and your network and your loads, they are all interconnected, and then your power network experience a wide range of disturbances. And thus here in this figure, it shows what could be the disturbance, and then the corresponding control action to be applied on the power network. And this is now referred or shown in terms of the time scale. So you can see here that if there is a fault, so if it is a temporary fault, let's say of your 50 millisecond or 100 millisecond or 150 millisecond, so your protection scheme should operate to isolate the fault in this range of millisecond. So thus the protection scheme is here. And then if you go next stage, so you have the voltage control on the generator, or it could be even on the bus as well. So this could be the range 1 second or maybe 2 seconds, or if it is referred as a short time voltage stability, so it will be for a few seconds, or maybe for a long-term voltage stability, it will be for in range of minutes as well. So this is the range of the in time scale, what is the voltage control being applied. Then for the power output control on the turbine side, so you can see this is the range of duration. So normally the turbine being mechanical system, and then they have inherently higher delay, and thus they are slower in action to control the output power. So it could be even as long as something 50 seconds as well, or you can say some few minutes here. Then if you refer to the load frequency control, which is in the secondary loop, and thus that has the information even about the Thailand power. In that respect, you can see that secondary loop for frequency control, it is it could be, because in this range it will be for primary frequency control, but for a larger range of time duration. So here it could be for few minutes to several minutes. So then it will be referred for secondary frequency control, secondary loop for frequency control. Then for a much longer duration, so you find here that for, let's say, for half an hour or 1 hour something, so there you decide, there you make a policy that which generator should be economically selected for the generation change. So in that case, how much should be the change in the power schedule or the power flow or the power supply in the network or from the generator side. So that will again at a much longer duration. So this is the complete range of control actions being applied in the network. And then again, you can see here it is in the wide range of time duration. Here, in fact, we have not shown the time scale for the lightning surges, but the lightning surges, they are in the time scale of microseconds, so but it's not shown over here. But protection is, again, it will be as a part of any disturbance that you have it on the overhead line due to the lightning surges. So again, let's say, for example, the surge arrestor, it has to operate in few milliseconds whenever you have the surges on the line, or the surge wave on the line. Then the next one, we move here to this slide. So I have then a little bit more about the generator control loop. So here we have the this is governor here, which is for speed, and then automatic voltage regulator for voltage control. So both the governor and the AVR, they are set for a particular operating condition so as to achieve frequency and voltage within the nominal value. And so here what we say that the governor actions and the AVR actions, they are applied at steady state condition, and mainly against small disturbances. let's say for example of load change. Now, as shown here, you have the generator, turbine, and the reference. So it shows here what will be the set point for the output power from the turbine or the generator. So this is the feedback to the governor. So this is one loop here. Then the generator has an excitation, the field circuit here, and then you have an AVR and reference set point for the voltage. And also you can see, in fact, it should be this direction here, this direction of the signal here. So you have the feedback of speed of frequency deviation here to the power system stabilizer. To again, it is in fact it is to be on automatic voltage regulator here. It should be basically it should be the diagram should be shown. Basically, it's like something here. It should be this one actually. So that should be the case here. So thus we have an auxiliary signal, supplementary signal being fed to the AVR section here for damping out the low frequency power oscillations here. Now, the first question should be why it is important to maintain the frequency. Because if your frequency dips, let's say goes beyond the 49 hertz something, because nominal frequency should be 50 hertz here, but if let's say frequency drops something in this range, then it may have some impact on the operational life of the turbine blade. And in fact, we have the use of under frequency relay, and because we don't want the generator and thus the turbine to operate at a lower or the if your frequency drops beyond the allowable range of frequency change, I mean. So in that case, we have the under frequency relay. So that may cause to trip the generator. And in some cases, we also have the use of under frequency load shedding. Again, a form of a relay circuit which will trip the load here. So you have the load shedding also applied if the frequency drops in a stepwise. So you cut the, you have the load shedding in the system with the frequency in the step form. Yeah, so that are the some of the approach that we can have, that we have normally in our system, so that the frequency does not dip beyond the allowable limits. But again, our objective has to be to restore the frequency back to the nominal value whenever it dips beyond the range, or if they normally if we require it to maintain within the nominal range, allowable range of 50 hertz here. So in terms of some components, as you can see, you have turbine generator, we have the measurement of the speed signal, and then you have the controller, which will feed the command signal so as to regulate the output power on the turbine or generator. This generator is subjected to, because the generator is connected to your power network, and then you have the load here. So you have some disturbance on the load side, and as well as there could be some disturbance in your network. Let's say you have a trip of the line, and in that case, this forms a disturbance on your generator. So against this disturbance, you have to control the output power from the turbine generator set. So now, as a simple form here in this figure, as you can see in the block diagram, so it is referred as this is for the hydropower plant. So you have the turbine, you have the generator, and then you have, let's say, some exciter. So as shown it here, it is a DC exciter and the generator is connected to a load, but we have not shown it, the generator being connected to a network, but it could be a local load as well. So this forms the hydropower plant. So you have that hydro turbine and then the guide vane, and then you have the water inlet from the reservoir through the penstoke on the guide vane. And thus to control the output power from the hydro turbine, you have the control action to the governor. So it could be PID control governor, which will have the action on the actuators. So here you have the servo motor. So here you can see for the regulation of output power or the frequency, you have the governor, and the governor has the feedback of speed signal, and this is your reference signal, or the set point. So this could be the scheme, or it is a general block diagram shown for hydropower plant, which is operated in an isolated system. So we have not connected the generator to your network. So you may have some local load being fed from the small hydropower plant. Yeah. So now, when the basic point we must remember when we talk about the frequency control, it is in terms of equilibrium of power. So whatever the power which is produced, and then that has to be consumed by your load, and also because you supply power through your network to the consumer. So that means the whatever the power which is generated, that should be equal to what is the power which is consumed, and then some amount of power loss that take place through your transmission or through your distribution here. Now, in fact, the power which is produced, that could be plus minus around a constant value. So you may have a constant steam inlet, or constant steam flow, or water flow to the turbine, and that could form some kind of stability, but obtained in a natural way. If we have the constant power produced, then in that case, that means if you don't have any disturbance in your network, so that will form a natural form of stability. So thus these are the important points which refers to the power equilibrium. Yeah. When we refer to the characteristic for the frequency control, we must understand what is the characteristic of our power network. So in fact, frequency deviation or the frequency variation around the nominal value, it depends upon the active power balance. So if there is a mismatch between your generation and the consumption, so definitely that will be translated in terms of some amount of frequency deviation. So any imbalance in your generation, any imbalance between your generation and the demand, basically it is reflected in terms of frequency deviation. And thus, when you talk about the power control, power generation control, and then the frequency control. So power generation, active power generation control, here it refers to, and the frequency. The both sometimes they are referred as load frequency control or automatic generation control. Automatic generation control, it will be when you talk about the set point for the scheduled power flow or the scheduled generation. So then it becomes a part of automatic generation control. Maybe later on we will discuss about what could be the difference between the LFC and the AGC here. Now, change in the active power demand, as I said, it will be reflected throughout the system. So that means a mismatch between the generation and the demand. You always get it in the form of frequency deviation. And that is, you can say, a good way of saying that uh, that there is whether there is a perfect match between the generation or the demand, or is a little bit of mismatch. So that is what we reflect in terms of frequency deviation here. Now, when we look at how does the, because you have to meet your generation as per the demand, and thus we like to know how does the load varies against the generation. So in fact, whatever the based on the consumption pattern of the power on the consumer side, when you look at they have changing. So you always have the consumption of electrical power from the consumer side varying. It is a time varying. It changes time to time. In fact, throughout the 24-hour, hourly, you can say you have an hourly variation of the power consumption, or in fact it is also daily. Let's say weekdays and the off weekend, off weekdays, weekend days, Saturday and Sunday, that could be, you have different pattern of consumption. And then again, of course, month wise, and when you go back to seasonal variation, so there could be a seasonal variation as well, let's say for the winter months, summer months, or the autumn months, and so on. So this earlier, from this point, it is clear that your consumption will vary, and thus the operating point for your system, it undergoes a change, and thereby causing or resulting into some form of frequency deviation. And thus you have to schedule your tile and power flow in your network when the system is interconnected. So but the total generation does not change in the step with the change in the load. Normally, let's say if unless you have a large change in the load, normally we find that load change they take place in a gradual form. So thus the generation change normally it does not follow a step change, but more or less like a gradual change. However, situation can become serious when you don't have your governors not in normal operation. So that could be a serious situation that may arise. So thus we have to look into account how effectively you design your controller, or you have the regulation of the frequency and thus the output power changer in the generator and thus the system. Now, when we if now it is clear that we have to whenever there is a mismatch, so this is translated in terms of frequency deviation. But frequency deviation, again, it depends upon some system behavior, some system parameters. And here we would like to understand how does the frequency change takes place, and what are the factors that influence the frequency profile, or the change in the frequency profile. Yeah. The first one refers to the load change here. How does the load change will influence the profile of the frequency variation? Now, what we say the load change, it is basically the difference of the demand and the generation. And we can say it in terms of percentage. So what is the percentage change in the uh, power demand? So we can write in this way. So this is the output power from generator. This could be the change in the load, and then as a percentage of power generation. So this could be the change in the turbine power or the generator power to be achieved here. And larger the change you have it here, more will be decay of frequency. I will discuss, that means I think, yeah, here I have it, so I will discuss later on. So you understand that more be the large change in the frequency, change in the power, uh, greater will be the decay in the frequency. That means more sharp change in the frequency you will observe. For if it is an isolated system, of course, due to the change in the load, this decay could be a little bit more because the system is if is not interconnected, and thus you don't have much inertia. And thus in that case, for mainly for isolated system, for let's say for 10% change in the load, the decay of frequency that we observe for isolated system will be comparatively more as compared to the interconnected system. I mean, so here it is shown. You can see we want to understand how the load change will cause the frequency variation. So you can see on this scale y-axis you have the frequency, and then here on the x-axis is the time in second. So if you have 10% load change, and again it is shown it for overloading condition, right? Let's say you have a rated load applied, but let's say you have more load on the generator. And this graph or the variation of the frequency profile is shown for inertia of 4 seconds and a load damping constant of 2 seconds here. So if you consider a 10% increase in the load, overload, then this is the decay in the frequency. But if it is a 30%, the change in the frequency, and 50% and 100%. So that means you double the load. You double the load of the generator. You can see that the frequency drops to 40 hertz here. And it is, and then frequency drops to 40 hertz in just in 6 seconds something. So here, this decay in the frequency, what we observe, that is the actually the initial rate of decay. So you can see that larger the load, the decay in the frequency will be more here. So then, but this graph is shown without regulation, without any governor action. So you have the increase in the load on the generator, and then you see observe what will be the frequency change. So you can see that this could be the steady state frequency value. Yeah. So this will be the steady state frequency value here, which you will observe in the system. So it is clear that a large amount of load will have a sharper change in the frequency profile. That means the decay fall. The fall in the frequency profile will be sharper when we have higher amount of load on the generator. Next one refers to the inertia. How does the system inertia will influence the change in the frequency? And this inertia, the system inertia, we get it from the rotating mass of turbine and generator unit. And in fact, the initial rate of decay of frequency for a given overload, for overloading condition. So it will be the, in fact, the inertia as well. What is the system inertia? Because if you refer this profile, we have shown it for a given inertia. So thus the decay in the frequency, what you observe, it also depends upon what is the system inertia. And thus that means the initial rate of decay frequency for a given overload condition, right? So it will also depend upon what is the inertia. Smaller the inertia, then the decay will be faster. And thus, if you have high inertia, so obviously the decay in the frequency will be slower. And thus, for an isolated system, that means the system is not interconnected to a large power network. So that we call it a small islanded system. So such isolated system will have small inertia, right? And thus, whenever you have the small inertia system, and in that case, the decay in the frequency could be more, and thus it is important that it will be much more challenging to obtain the frequency regulation for an islanded system because the system inertia is low, and thus it will be challenging to regulate the frequency for an islander system here as comparable to the interconnected system here. So we continue, and what we discussed, it was about the how does the inertia, what is the impact of system inertia on the variation in the frequency. So with this, as we move to the next slide, so here you can see on the y-axis you have the frequency, and then x-axis is time scale, and this is shown for given load damping constant and then load change 50%. It is over, that means 50% more load on the generator. So you can see the profile of the frequency change, and it is shown for this one for 7 seconds, and then much lower, that's a 4 seconds, and then much lower 2 seconds. So you find that if the system inertia is low, then you have a sharp decline, sharp reduction in the frequency profile. And thus you can say the rate of decay in the frequency here depends on system inertia as well. So more higher the system inertia, then the decay, as you can see, it is comparatively less. And if you have low inertia, then you find more decay in the frequency. That means the frequency will dip from 50 hertz, let's say something 42 hertz in a shorter time frame, about 8 seconds here. It's dips. Yeah. But if you have higher inertia, then the decay will be a decay of frequency to 42 hertz something. It will be comparatively slower, and thus you may have sufficient time to apply any control action when you have the frequency regulation considered in the system. And thus for an isolated system, if you refer on the previous slide here, so as I said, it will be much more challenging because the system has low inertia, and thus it will be much more challenging to restore the frequency back to 50 hertz in a short, because in shorter time it decays down, and then it will be challenging to achieve the frequency restored back. if you have low inertia, and more specifically for low inertia or islanded system here. So we move to the next slide now. So we have it here. So this is the next slide. And here we discuss how does the self-regulation will influence the frequency variation. And we have discussed two factors. One was the last one, what we discussed, it was the system inertia. And the first one, what we discussed, it was a load change, how much load increase will influence the frequency variation. And the third one, now we discuss how the load damping factor, which I think earlier also we have some discussion, how does the load damping factor will influence the improvement. Perhaps it is a improvement, and that's why it is referred as load self-regulation. So when we have the system frequency decay, demand will decrease. That means this demand decrease we experience mainly from dynamic load, which could be a motor load. So that means when the frequency has dropped, then the power drawn, the torque developed by the motor is a factor. That means it is reduced, and thus the power drawn, or that means the demand by the motor at a reduced frequency, it is comparatively less. So in this way, the dynamic load, they act as self-regulation in a say that when the frequency decays, the demand reduces, and thus the behavior or the characteristic of the torque slip characteristic for the motor, induction motor, it acts as a self-regulation phenomena so as to improve the frequency profile. That means to minimize the decay of the frequency. And to take into account this behavior from the dynamic load, we have it a factor which we call it as load damping factor, and this is how they are related. So it is you can say what is the amount of change in the load to the initial load or the nominal value. So D is basically, you can say, the percentage change in the power to the percentage change in the frequency here. So that's the load damping factor here. So we move to the next, this one. So as you can see here, we have this frequency profile plotted for different value of load damping constant. So you can see if you have higher value of D, so that means more in the industrial load, more basically from induction motor. So if you have more induction motor load, so in that case, the decay in the frequency, the initial decay, and then if you have less amount of load damping constant, so here you can say this is the decay. So if you have low value of load damping constant, then the decay in the frequency will be sharper. So that means you have more decay in the frequency. So it is preferred that the power system should have sufficient amount of dynamic load, mainly from the induction motor, so that we have good damping factor, and thereby thereby load damping constant, I mean, not the damping factor. So that we have good load damping constant, and thereby slower rate of frequency decay, and thus the controller will have sufficient time to improve the frequency profile, and thus the frequency regression, because the controller action time involved in the action from the controller output signal, I mean, that again it is also important. So in that sense, if you have good load damping constant, then even if you have slower action from the controller, it will be possible to have sufficient effective, you can say, effective control towards frequency regulation. So that's what is the purpose for frequency control. We want to balance. We want to keep a balance between the demand and the generation side here. So in fact, because it is, we don't have any much control on the consumer side, on the load side, but we want to have the generation met against the variation in the demand here, basically. So thus we have to keep a balance, the balance of generation against the demand here. And this the balance, active power balance, here we measure it in terms of frequency for the system. So you can see here in this plot, the first curve, which you have it here, this one. So this is the case where you don't have any regulation applied in the system. So that's whenever you have a load increase, so frequency will dip and then settle down to some steady state value. But if you have some amount of regulation in the system, so for the same amount of, let's say, the load change, frequency will decay. If there is a dip here, you can say that is the maximum frequency deviation. And this sometimes we call it as nadir. So here, this is the maximum frequency deviation. And then with the regulation applied, you are able to improve the frequency profile. Then in fact, instead of having a steady state frequency, we are able to have the frequency improve. But still, you have some deviation at a steady state condition being observed. So even in this case, though, we have an improvement in the frequency profile over the time, but there is some deviation. So we have to work out how this frequency can be restored back to the nominal value. So you can see that if you don't have any regulation, so if you have 10% change in the generation, that means loss. Let's say demand is constant, but the loss, you don't have much generation. So 10% loss in the generation will result into frequency dip in the range of 3 to 5 hertz within a minute. So you can say that if in 1 minute, if this much change in the generation loss takes place, so frequency will dip from 50 hertz to 47 or 45 or something. But normally, that is what we normally apply in the system. It is this one. So maximum allowed deviation, normally we keep it in this range. It will be plus minus in this range, and thus we want to have some regulation on the system. So when you talk about the regulation of the frequency profile, so that means we say control of frequency. And that will be 2 ways. So, but most effectively, which we use or which we apply in the system, it is through governor action. So you have an automatic control of generation so as to match the generation against the load and maintain the frequency. In some cases, we also adopt under frequency load setting. So that means you don't have sufficient generation available, but you find the load has gradually increased. So then in that case, we may have the load setting, that means stripping out some non-priority load. That could be done, and then that means in a discrete form. So in a stepwise, we can have the automatic setting. This will be through relay operation. So you may have the automatic cutout of the some percentage of the loads in a discrete steps, basically, so that we are able to avoid the system collapse. So that is our main intention here. So thus the frequency of the system depends upon the balance between the active power, balance of active power, basically. And changes in the real power will affect your system frequency. And thus you can say the frequency will be a common factor. Throughout your network, a change in active power demand at one point, it will be reflected throughout the system because the system is interconnected. So if there is a mismatch of generation and demand, it could be at one location, but it will be reflected in the entire system, because the system is interconnected. So any mismatch at a local point or in a given area, it will be reflected in the form of frequency deviation throughout the system. So when we have an interconnected system, then we have two or more independent control areas. So here we will define what will be the control areas, which will be in operation to control the frequency, and then the generation within those areas, within each area, has to be controlled so as to schedule the power flow through the tie line. So that means you may have several interconnected areas, right? But we will have two or more control areas to have the change in the generation, and thereby the demand being met, and thus that is to say, to maintain the scheduled amount of power flow through the tie line that connects the areas. So there are several generators in the system. So some of them need to have an allocation of the generation. So that's some generators will be decided that which of those generators will be allocated for the change in the schedule generation against the demand here. What that means, for that generator, one will be the local speed control, which will be the primary speed control, and another one will be the supplementary control, that is the outer loop control here. So that's just to show how the governor works, basically. So whenever this is the case of a mechanical type of hydromechanical governor. So what you also that there is a fall here, and then as a result, what you find here that the piston is pushed down. This piston is pushed down, and then you have the pump of oil through this piston on this side of the valve. So this is the relay, basically, or servo motor cylinder. So as a result, it will push this piston on the left hand side, and thereby allow the more opening of this needle, and then you have more steam inlet or maybe the water inlet to the turbine section. So As you can see here, in this case, we call sometimes we say the throttling of the governor valve. So that means you throttle that means you position the valve here so as to have the steam inlet or the water inlet to the turbine section. And you can see that in this case, we have the movement of the piston to the left-hand side and thus more opening. So that means you have more steam inlet or the water inlet to the turbine. And this is the case which you observe when you have the fall in the speed here. So this could be like a speed sensor here. So when the speed falls, then this rotating ball, the fly ball, so because due to the centrifugal forces, they will reduce, and thereby this needle will go down, and then it will cause the movement of this piston downwards here in the main cylinder. This is the main control valve here. So this is the typical picture of the speed governor that we have in the power plant, and then spear valve to have the allow of jet. It could be for water jet on the turbine section here. So basic function of the governor, what we have it on the turbine, that is basically the prime mover. It will be to regulate or to change the power output from the turbine. And in an interconnected system, with the use of these governors, they will also allow stable parallel operation so that we can have sharing of load between the generators here. So thus these governors, they act to regulate the output power from the turbine and as well as have the sharing of the output power between the generators. So as you can see, here we talk about the primary control. So you have the generator coupled to your grid. I mean, it is electrically coupled, I mean here. And then here it will be mechanically coupled to the turbine. So you have the measurement of the speed, you have the governor, a reference speed, and then the throttling of the valve. So as to vary the steam inlet to the turbine here. So that is what we have it in the primary control. So maintain a balance between the generation and the demand, which you could obtain it from the network. And just the primary control loop, which you have it here. Remember, it works so from 4, 5, 6 seconds up to 10 seconds, 12 seconds, 20 seconds, and so on. So tens of seconds here. So that's the time of action for the primary controller. It is less than 1 minute, but few tens of seconds, you can say. Here it's shown as a block diagram. So you have the turbine. This is the feedback here for the speed signal through the transducer. And then you have a comparator where you get your set point. You have the droop because you have to have the power sharing between the generators. So we apply a droop here and then some kind of control design. It could be in the form of some compensator here. We have a power point, should be the reference power being set, but again, it depends on, then it is on the actuator. So in a more simple block diagram, you can say this is the generator connected to a load, then you have a turbine, you have this measurement of speed, and then the governor action here. So you can see this is the turbine torque, mechanical torque, the mechanical power. This is the electrical power, or you can also have electrical torque. and then the load power here. So with this, we want to work out what will be the model of the system. So following this basic relationship between the power and the torque, that is how they are related in terms of rotary speed for the turbine generator side. When the system is at a steady state condition, and then let's say you have a rated angular speed. So this is the rated speed. So this is 1 per unit. Then the mechanical power and the electrical power, both are its initial nominal value. And then this is how we can define in terms of torque and speed, and then they are equal. So when the machine is running at a rated speed 1 per unit, then the torque, you can say, and the power, they are same actually. But if there is some disturbance, so let's say a small change in the mechanical power, and then same way you have it on electrical power, a small change, and then this is translated what you have it in terms of torque. Yeah. So this is small change in torque, mechanical torque, and the electromagnetic torque. Now we take out the difference. This will be the power. Remember, you will get it on the generator output here. So PE refers to the electrical power from the generator output, and thus we can say the load here. But the mechanical power, what you have it is from the turbine side here. The turbine mechanical torque or the mechanical power. And thus the difference between the electrical power and the mechanical power on this side. So you have this one. And then the change in the power on the two sides. Now we write in this way. And then finally, we can equate it in this way. So what we also that this is how we write down in terms of the power and the torque. And then we write down the inertia model for the generator. So this is it now. That is twice of inertia, system inertia, then the differential of the change in the speed, rotary speed, angular speed, rate of change of angular speed, and then in terms of change in the or the mismatch in the torque or the power here. So this is what we say in terms of small change in the power, mechanical power, and the electrical power. That will, so this is this mismatch between the load side and the turbine side, that will cause the deviation or the rate of change of frequency or the angular speed here. And then in terms of angle, rotor angle, this is how they are related here. So you can see that 1 by omega naught, rate of change of angle, rotor angle, it is now related given as what is the speed deviation there. Then in terms of load model, this is the electrical power, and then here the load is considered to be a composite of two types of load. So one, this part, this term which you have it is frequency insensitive load. So it could be like those of non-dynamic load. So it could be like a lighting load. So they are, since they are a static load basically, so they are frequency insensitive load. But those which are like induction motor load, so they are dynamic loads, and thus here they have the load damping constant introduced. So thus they are referred as frequency sensitive load here. And this is how earlier we have said that what is the load damping constant. So what is the percentage change in the load to percentage change in the frequency here. So from the previous relationship, here we have written down the equation in terms in time domain, but this time domain term can be written down as a Laplace form. So we have it this way. So we have it, this is the change in the power, and then this term, what we have it. So this is the electrical power. So we have written down in this way. So we substitute over here. Then we do some manipulation. So because this side we have dial omega and this side we have dial omega. So we bring it to this side and then we have it written out. So now this quantity, what we have written down, it is in this thread. So this is the mechanical time constant, that is twice of inertia. Yes, and this is the load damping constant. And then you have it at the output, dial omega, this one. And this mismatch power, it is here. So you have the load change negative, and this is the mechanical power. So this load change can be positive or negative here. So next one, we have the what is the primary speed control, and here we talk about the isochronous speed governor. So in this case, we have included integral controller so that we get a speed, or there's a frequency restored to the nominal value. Otherwise, following the load change, there will be a residual frequency error. So this one, what we have it, is not for multi-machine system, and it is referred here when we have the generator supplying power to a local load. That means when the system, when a generator, it is with a local load, and that means the generator is not connected to a large network. So it is as an isolated system. So that's why it is referred as isochronous speed governor. In this case, you have one generator in the system which will be required to regulate the frequency against the load disturbance. Now for that means for isochronous governor, you have the generator, you have coupled to the turbine, and then the measurement of speed, the comparator. Here you have the proportional controller, you have integral controller, and then to regulate the valve position here. So in the case of isochronous speed governor, since you have the integral, it will, as you can see, this is the speed. So whenever you have a load increase, right? Whenever you have less load increase, frequency drops here. But because of the proportional and the integral controller, rotor speed is restored back to the nominal value. And since you had the load increase, thus the turbine power should also increase. And in that case, this is the turbine power. So this was the initial power. That means the turbine power at the steady state condition. And following the load increase at this instant of time, you have the increase in the power that will be through the governor. So you have the increase in the power, and then it settles down to this value. So this will correspond to the amount of change in the load on the generator, and that should be equal to the change in the power. So that means increase in the mechanical power is equal to the increase of the load, and that's why you have the speed restored back to the nominal value here. So in the case of isochronous speed governor, as you can see, that means for isolated system, you can see that it is possible to restore the frequency back to the nominal value here with a local loop controller, Now, again, another objective for the governor was to have power sharing between the generators, and thus we apply a speed droop on the governor. So this droop, as I said, it is for load sharing. So the proportional controller, it is given with a gain of 1 by R. So R is the droop here on the governor. So it refers to percentage regulation for the generating units to be equal, and that is the change in the output power for each unit. This should be proportional to the rating. So that means the regulation that we apply for each of the generating units to achieve the change in the output power will depend upon what will be its rating. So that means the R value will depend upon what is the rating of the generator unit here. So thus we have the speed load characteristic to be applied on the governor setting. And further, as you can see, when we have the primary control loop, the governor with the speed loop. So what you find it here, at the output of integral, we have applied a loop here, which is again fed back here to the summation. So thus, this is how it is related. So what is the output power and the, in fact, from the integral output basically. So this will be the input to the R here. And then the output of the R is your speed deviation here. So this part, what we have, this part we can manipulate now, and we have it shown in this figure. So you can say the integral. So this is the summation here. So it is this one. So you have dial omega R here, integral gain, the proportional gain, the integral gain, and the output here. It is the actuator position. It is this one. And then this is the feedback. So you have this feedback here of regulator. I mean the loop here. So it is given here. So we have modified this. We have represented it here, and then we will modify this block diagram as in this figure. So we have dial omega, and then this is minus and minus here. So here we have 1 by R. So that will be the gain here. And then, in fact, we have written down in terms of the time constant here for the governor. So it is 1 by 1 plus Tz here. So that is dial omega R here. So now this Tg is 1 by Kr here. We have manipulated this one actually basically, and then we have written down as a first order system. So what is Tg? This one. So we manipulated this quantity, and we have reduced this block diagram as a series cascade form. Yeah. So thus the output here, what we get it, that is the from the first order model for the governor. So that is the output power that we apply, and then you have it at the feedback. That will be, you can see this can be the feedback. So it can be from the speed here, because when you go back here, this one. So this can be from the speed. So we have it here. Then in fact, the same previous block, it is actually manipulated. So we have written down, because we know the relationship between the speed and the power in terms of R group here. So we have manipulated this the previous block diagram here. Then what is this output? So we write down in this way. And the difference of the two, it is here. So P reference, and then 1 by R times dial omega R. So it is this way here. So this is how we define the speed regulation or the loop. That is basically the what is the percentage change in the speed or the frequency to the percentage change in the output power here. That is, you can say, change in the speed from no load to full load expressed as percentage of the nominal speed here. So the governed load group, normally it is in the percentage, and if I say a 5% group, or say regulation of 5%, it means it will cause a 100% change in the output power. So a 5% change in the frequency will be observe for 100% change in the power from this kind, that means from no power, 0 power to 100% power, will result into 5% change in the frequency here. So that is something like this. So you have the frequency. So this is the no load speed, and this is 0 power. And if the power is increased to 100% unit value, then the change in the speed from no load to full load. This is the full load speed here. So change in the speed from no load to the full load, that is due to change in the power by 100% here. And thus this is the droop characteristic here, which is a negative slope characteristic. And this is how now we can say what is the droop. So this is how we define what is the change in the frequency, what is the slope of the curve, the slope of this characteristic basically. So the frequency deviation, ratio of the frequency deviation to the deviation in the power here. This way. Then when we want to apply this for the sharing between the generators. So as you can see, this is the generator 1 and generator 2, unit 1 and unit 2. This is the characteristic you can say. Here you can find that there is the slope of the characteristic. And here you find this is the slope of the characteristic. This is much more steeper. You have much more steeper in the curve here, much more steeper in the line curve, the slope. But this is somewhat flat, you can say. And thus, more steeper curve, you will get it for smaller rating of the generating unit. So a smaller size of the generator will have more steeper curve. But if you have a large size of the generator, then the curve will be not that much steeper. So thus, if you want to, this is the nominal frequency, you have it here, this one. And if you want, let's say for the same amount of the load, constant load, but let's say you want to increase the sharing, or the, I mean to say change the sharing between the generator. So at the nominal frequency, this was the output power from unit 1, and this was the output power from the unit 2. But let's say you want to have more power shared by unit 2. So let's say the change in the frequency here, and then the change in the power from unit 1 to this quantity, and then for this quantity for generator 2 to this quantity here. So you find here that for this defined frequency deviation, for this defined frequency deviation, as you can see, this unit, this generator will have more power here with respect to this generator, because you can see the change in the power. Here it is lower, but here the change in the power will be more. But here we talk about for the same frequency deviation. So thus you can have the sharing of power between the two different generators, and that will depend upon what is the droop characteristic. So thus the change in the power from generator 1 and generator 2 will depend upon what is the droop characteristic for each of the unit. And you can see that change in the power or the load sharing is inversely proportional. They are inversely related here. Now, if we want to have the speed and the power drawn for this case, so with primary loop control, so if there is a sudden load increase, you will find the drop in the frequency, decay in the frequency, but due to the controller action, governor action, you can see the speed is restored back. But again, there is a steady state frequency deviation here. You have a corresponding increase in the power, turbine power here, and this is the increased amount of the power. But still in this case, when you have two generators operating in parallel, and when they are of different rating, so you have a steady state frequency deviation here. right? So maybe I will stop here now.